All right, hello guys. This is the math portion of the ecology unit, and it's not too bad. There are a couple equations we have to know how to get through, but basically it's just looking at the ecological content and putting a math equation or a math purpose to it. So one of the things we were talking about with biomass was the concept of how much like organic material there is in an environment. With this is gross primary production and net primary production. They recently took this off, I think, but I still like to just kind of review it real quick because it's a good kind of thought process to know how to kind of get through. But basically, what it is the total or gross primary production is the total primary production of an ecosystem. So this is all of the producers in that ecosystem. So you can imagine like a desert's not going to have a very high gross primary production, while the like rainforests are going to have a much higher or primary production there. And this is due to a lot of factors like water, heat, temperature, sunlight, things like that. The net primary production is the gross primary production minus the energy that the organisms, those primary producers, are going to use for respiration, which is R. So if we look at our equation, it's pretty easy. But if we look at it, NPP, that's the net primary production, equals GPP, which is a total primary production minus the respiration. So usually what they'll do is they'll give you two of these parts, so either the gross primary production and the respiration, or like the net primary and the GPP or the R, and you have to figure out what the other one is. It's pretty easy. It's just kind of fill in the blank and figure out the last part of the equation. Ecological efficiency. So when we talked about the food pyramids and the different trophic levels, you have a different amount of ecological efficiency. So you can see here we have plants that produce this much. We have insects, fishes, and then top level fishes here. So basically, all you have to do is you have to take the trophic level, the next trophic level, and divide it by the last trophic level. So for this first one, all you're going to do is you're going to take 3,368 divided by 20,810, and that's the efficiency of the next level. And you just put or write that as a percent. So pretty easy to see how we go from next level to next level. We talked about the 10% rule and saying that hey, every level you're going to see about 10% of that energy efficiently being transferred to the next level. It's not perfectly 10. Again, nothing in life is ever going to be that perfect, but the roundabout is around 10. So you're going to see the average number between each level is about 10%. Usually at first level, it's a little bit higher, and then at the last level, it's not as high. So it averages out to about 10%. All right, so this is where one of the equations that is a little bit difficult. This is called Simpson's diversity index, and basically what this looks at is how biodiverse a ecosystem is. If you look here, which ecosystem is more diverse? Between A and B, you're probably going to say A is more diverse. You can see B here. Yes, we have a couple other species, but it's mainly this regular looking tree here. And we use this equation here in AP biology. There's another equation I've seen used as well, and it's very similar to this, but only focus on this one. This is the one they give you on the formula sheet that the AP Central will give you. But it's basically the biodiversity index equals 1 minus the sum of n, which is the total number of organisms in a particular species, and n, the total number of organisms of all the species. And we have to do this for each species. And I'm going to give you an example of this going forward here. Oh, by the way, a high value of D suggests a stable and ancient site. So like a site that has been there for a very long time, that's very, very, very biodiverse. A low value of D could suggest like pollution, things that are like colonization, agriculture management. So things that are going wrong in the environment. Just the like the push of a environment to it's not good for the environment. So a lower diversity index is just not good. All right, we already went over this. Yep. Okay. So biodiversity index here, you can see here we have three different species, 325, 305, 370. So what you do is you just place each one of these into into the equation. When we add all these up, it comes out to a really nice, easy 1,000. You won't always have that, but that 1,000 goes here on the bottom, and you do square both. So like these parentheses should be technically around both of them, but with program, it's really hard to write. So you square both, which to make it easier, we have to square this bottom, and they're all the same. So it's going to be 325 squared plus 305 squared plus 370 squared all over a million, because 1,000 squared is a million. That's going to make a number here that is so smaller than 1. So we take 1 minus that number, and we're going to get 0.664. Okay. Right, the last mathematical thing we're going to be really working with is exponential versus logistic growth. And basically, exponential growth is your rate of your growth, or the growth rate of the population times the actual population size. You can see here we have the just another like what how exponential growth of that growth is signified. It's when you ever see d of n or divided by d of t. It's just pretty much saying like what's the growth of the population. So we have the growth rate, we have the population size, and to find the growth rate, you can see here R equals birth rates minus death rates divided by population. We can find that pretty easily. Now, a population that has 10 rabbits during the breeding season, 5 of the rabbits are born, however, 2 rabbits die. What's the population growth of this population? So we have the n, which is the total number. We have the births, which is 3, deaths, which is 2. So if we take 5 minus 2 divided by 10, our growth rate, or R, is 0.3. So then what we can do with that, all right, so what you do then is you take your growth rate and you multiply it by your population and you get 3. This is pretty easy to start us off, but it gets a little bit harder with the logistic growth, which there's a different equation. So you can see we have that original exponential equation, but then we're adding in the k, the carrying capacity, minus n, which is the population, over k. Now let's do this again for another population. If population has carrying capacity of 900 and the growth rate is 1.1, what is the population growth R when the population n is 425? So you can see here, all we're going to do is we're going to plug in this information. R is 1.1, N is, where's N? N is 425, K here, the carrying capacity is 900. So you can see here, we're just taking 900 minus 425 over 425. Then we're multiplying everything together, and we're going to get 522.5. So that's the population growth that's going to occur after, or differently than the exponential growth. So basically, that's all the ecology you need to know for the math portion of AP Bio. So good luck.